So let's talk about what it means when you write down a value with its uncertainty. So I've got a list of data here, and they all have the same size uncertainty, 0.20, but the values are different in each case. So it's very common in the sciences that you would have two values, for example, a value that you measured experimentally and another value that you calculated theoretically, and you'd want to say, do these two numbers agree with each other? Well, the real question is, do these two numbers agree with each other within their limits of uncertainty? So let's look at this first data point, 9.20 plus or minus 0.20. So what does it mean when I write a value with its uncertainty like this? Well, it means that you're confident that the true value, whatever it is somewhere in this range, from 9.2 plus or minus 0.20. So when you write a value with its uncertainty, you're specifying a range of values. So now let's compare this data point to the second one, B. So B is 9.50 plus or minus 0.20. So I've centered the data point on 9.5 and added in my arrows for plus and minus 0.20. So ask yourself, do these two numbers agree with each other? 9.2 and 9.5 are obviously different, but they both have uncertainties, and the uncertainties actually overlap with one another. So again, do these two numbers agree with each other or not? The answer is yes. If the two ranges touch each other or overlap, you consider the two numbers to agree within their limits of uncertainty. And you should remember that phrase, they agree within their limits of uncertainty. That's how you'd phrase it in your lab report. It also counts if the two ranges just touch each other. So for example, if I compare A and C, C is 9.6 plus or minus 0.20, and again, because these two ranges of data encompass the same point, we say that yes, they do agree within their limits of uncertainty. So 9.2 plus 0.2 gives you 9.4, and 9.6 minus 0.2 also gives you 9.4. So now let's look at a case that definitely doesn't agree. Let's compare A to D. So D is centered at 9.7 and again has an uncertainty of plus or minus 0.2. And as you can see, there's a little gap between these two ranges. So that gap is crucial. If the two ranges don't touch or overlap, then these two values disagree within their limits of uncertainty. So up to now, we've just been eyeballing it and saying, okay, do these arrows touch each other or overlap? You can do all of this mathematically. So the fastest way to check whether two values agree within their limits of uncertainty is to see whether they satisfy this inequality or not. So what this equation means is you take the difference between the two numbers, and you see whether that is smaller than or equal to the sum of their uncertainties. So for A and B, the difference between 9.5 and 9.2 is 0.3, and the sum of their uncertainties is 0.4. So this inequality held. The difference between the two values was smaller than or equal to the sum of their uncertainties. In the case of values that don't agree with an uncertainty, you'd find that wasn't true. So I've compared A and D in this example. So the difference between 9.7 and 9.2 is 0.5, but that's bigger than the sum of their uncertainties, which is still only 0.4. So it's acceptable to judge this either way. You can either think about arrows on a number line and just ask yourself, do these two ranges overlap? Or you can work it out mathematically using this equation. So before I begin, I better first explain what the difference between agreement and precision is. So agreement refers to whether two values agree with each other within their limits of uncertainty. So it's a simple yes or no answer. Precision refers to how accurate a value we're capable of getting using the current equipment and the current technique that we're using in this experiment. So it's a little bit more involved. It's all about analyzing which uncertainty affected your final answer the most and how you could make that better. In your lab report, you're going to be asked to do a precision analysis on your final answers. Now, the first step in any precision analysis is that you want to look at the uncertainty formula for your final expression. So let's say that this was the equation I used to get my final answer. I want to look at the uncertainty for this expression. Now, I'm going to make this just a little bit more complicated in that this V is not going to be something that we measure directly. It's something that we calculate from other measured values. Specifically, V is going to be equal to D over T, and this will become relevant later. Right now, however, we're going to start doing the precision analysis on this expression for the acceleration, A. So as I said, the first thing you do in a precision analysis is you want to look at the uncertainty expression for your final answer. So let's calculate that now. So the uncertainty for this is going to be the final answer times the square root, and then I'm going to have three terms, one for V squared, one for the 2, and one for D. So this is the uncertainty of V squared, determined using the roots and powers rule, divided by V squared. So uncertainty of V squared divided by V squared. The next term is the uncertainty of 2, a constant, divided by 2. And the third term is the fractional uncertainty of d, the distance. Now there's some simplifications I can make here. For starters, the uncertainty of a constant is just going to be 0, so this term is going to disappear from our expression. Secondly, the v squared on the top and the bottom of this first term are going to cancel out with each other. So now let me write down the simplified version of our uncertainty expression. So this is what it looks like, and this is what we'll proceed with. Now our first job in a precision analysis is that we want to find out what uncertainty affected our final answer the most. In other words, we want to find out which of these terms inside this square root is the biggest. So to figure that out, we're going to need to actually add in some values. So let's say that these are our values. We're going to substitute v and its uncertainty into this first term, and d and its uncertainty into this second term, and see which one gives a larger value. So I'll do that now. So the first term is 2 times the uncertainty of v divided by v, which I've calculated down here. I substitute in values and I get an actual number. The next term is the uncertainty of d divided by d. And again, I substitute those numbers into the expression and actually calculate a number for it. And once I've done that for these two terms, I can just compare these two numbers. Which one is biggest? Obviously, it was the term that involved v. Now, if v was a measured quantity, then we'd be done the first part of our precision analysis. In our report, we'd say v affected the precision of the experiment the most. However, remember that I said that v was a calculated value. That means we need to drill down farther. We need to look at the uncertainty expression for v also and figure out which measured value affected its precision the most. So if in the original expression everything in it was a measured value, no calculated values, then we just need to figure out which term was biggest, and then in our report we could say, this is the uncertainty that affected my experiment's precision the most. However, because the term that was largest in this case is a calculated value, we have to go back farther and figure out which measured value affected its precision the most. So I'll do that now. So you'll recall that the expression for v, the final velocity, was this, small d divided by t. So the uncertainty for v is just going to be the final answer times the square root, and inside we have a fractional uncertainty for each of the two measured values. So now we do exactly the same thing we did before. We're going to substitute values into these two terms and see which one is biggest. So let's say that these were our two values for d and t. So we're going to substitute d and its uncertainty into the first term, and t and its uncertainty into the second term. So that looks like this. Substituting the value and the uncertainty of d into its fractional uncertainty, we get this value. And substituting t and its uncertainty into the expression gives us this value. And again, we just need to figure out which one is biggest. So obviously, it's the fractional uncertainty of small d. So in your report, you would say d affected my experiment's precision the most. Now the first half of your precision analysis is always to get to this stage, where you know what quantity affected your precision the most. The second half of your precision analysis is then to suggest a way to improve the precision of this one measurement. In other words, you want to make this number smaller somehow. Now in our case, we've got just a very simple fractional uncertainty here. So there's only two ways to make this number smaller. Either our uncertainty gets smaller or the value itself gets larger. Now students often immediately try to think of a way to make their uncertainty smaller, but it's often easier to think of a way to make the value itself larger. So for example, you could try to think of a device that would give you a smaller uncertainty when you're measuring the length of the glider, or you could just use a longer glider, because then your uncertainty would remain the same, but the value would get larger, and that would make your fractional uncertainty smaller. It is possible to come up with suggestions for how you make your uncertainty smaller. So for example, if you had a large source of physical uncertainty, maybe you could think of a way to eliminate that. Alternately, you can suggest a specific device that would give you a smaller uncertainty. So you might say, I could use digital calipers to measure the length of this glider, because that has a much smaller uncertainty than the ruler that I did use. So either way is acceptable. You can either suggest a way to make the uncertainty smaller, or you can suggest a way to make the value itself larger, which is often easier. So all that said, I want to point out that there are situations where you can't suggest a way to make the value larger because it wouldn't help. So for example, let's say that d did not turn out to be what affected our precision the most. T, the time, did. And furthermore, let's assume that we measured that time with a photo gate, which has an uncertainty of 1%. So the way in which you calculate 1% is 0.01 times the value. It gives you 1% of that value. And so now you see why we have a problem, because if we come up with a suggestion for how to make t larger, it's just going to get cancelled out by the t up top. So 1% of a larger value is still 1%. So this is a case where we have to come up with a way to make our uncertainty smaller. So one suggestion that often helps with this is you could say, I'd measure the time value several times, and then I'd calculate the statistical uncertainty. I'd use that instead of 1%. Because you'll recall that statistical uncertainty is 2 times the standard deviation divided by square root n, where n is the number of trials that you average together. So the nice thing about statistical uncertainty is the larger n gets, the smaller your uncertainty gets. So that's a way to control how big your uncertainty is. You can just take an average of more values to get a smaller uncertainty. So let me now summarize. For your precision analysis, the first thing you do is identify which quantity affected your precision the most. That means you look at your uncertainty expression and you figure out which term in it is largest. The second half of your precision analysis consists of coming up with a hypothetical suggestion for how you could redesign the experiment and make your precision for that one measurement better. In other words, how to make that term smaller. So if we had determined that the length of the glider d was what affected our precision the most, then a good precision analysis to write in your lab report would be something like this. The length of the glider, d, was found to affect our experiment's precision the most. To improve this, we would use a longer glider, which would reduce the size of our fractional uncertainty. Alternately, you could also suggest a way to make the uncertainty of this measurement smaller.